Mastering deep learning. Neural networks harbor secrets in their architectures, waiting to be uncovered. Where do the underlying differences lie between a deep neural network utilizing a recurrent architecture, one employing a convolutional neural network, and another leveraging a transformer-based architecture, specifically in terms of their functionalities, strengths, and limitations within the realm of deep learning? In the realm of deep learning, three prominent architectural paradigms have emerged: recurrent neural networks, RNNs, convolutional neural networks, CNNs, and transformer-based architectures. While they share the common goal of modeling complex data distributions, each architecture is uniquely suited to tackle specific problem domains, exploiting distinct strengths and compensating for inherent weaknesses. Recurrent neural networks, RNNs. RNNs are designed to handle sequential data, where the relationships between consecutive elements are crucial. Their core strength lies in modeling temporal dependencies, making them ideal for tasks involving 1. Sequential data processing. RNNs are well suited for handling data with temporal or sequential structures, such as speech, text, or time series data. 2. Language modeling. RNNs can capture contextual relationships in language, enabling applications like language translation, text summarization, and chatbots. The primary components of an RNN include recurrent connections. Feedback connections allow information to flow from later time steps to earlier ones, enabling the network to maintain a memory of previous inputs. Hidden state. The internal state of the RNN, which captures information from previous time steps and influences the output. However, RNNs suffer from vanishing gradients. Gradients used to update weights can become smaller as they propagate through time, making it challenging to train deep RNNs. Exploding gradients. Gradients can grow exponentially, causing instability during training. Convolutional neural networks, CNNs. CNNs excel in image and signal processing tasks, exploiting spatial hierarchies and translational invariances. Their primary strengths lie in 1. Image and signal processing. CNNs are unparalleled in image classification, object detection, and image segmentation tasks, as well as signal processing applications. 2. Translation invariance. CNNs can learn features that are invariant to small translations, enabling robustness to image transformations. The core components of a CNN include convolutional layers. Feature extraction is performed using filters that scan the input data, capturing local patterns and spatial hierarchies. Pooling layers. Downsampling reduces spatial dimensions, increasing translation invariance and reducing the number of parameters. CNN's limitations include limited receptive field. Each neuron in a convolutional layer only sees a small region of the input data, limiting their ability to capture long-range dependencies. Computational cost. The large number of parameters and computations required for CNNs can be prohibitive for large datasets. Transformer-based architectures. Transformer models, introduced in the context of machine translation, have revolutionized natural language processing tasks. They operate on sequential data, but without recurrent connections. Instead, they rely on 1. Self-attention mechanisms. Weights are computed as a function of the input, allowing the model to attend to different parts of the input sequence simultaneously. 2. Multi-head attention. Multiple attention mechanisms are used in parallel, enabling the model to capture diverse aspects of the input. Transformer strengths include parallelization. Self-attention enables parallel computation across the input sequence, making transformers more efficient than RNNs for long sequences. Global understanding. Transformers can capture long-range dependencies and model complex contextual relationships. Weaknesses of transformer models include sequence length limitations. While parallelization is efficient, it can lead to memory and computational constraints when dealing with extremely long sequences. Computational cost. The self-attention mechanism can be computationally expensive, especially for longer sequences. In conclusion, each architecture has its unique strengths and weaknesses, making them suited for distinct problem domains. RNNs excel in sequential data processing and language modeling. CNNs dominate image and signal processing tasks, while transformer models have become the de facto standard for natural language processing tasks. Understanding the underlying differences between these architectures is essential for selecting the most appropriate model for a given problem, ultimately leading to better performance and more accurate results in deep learning applications.